Hi everybody, welcome to week 3. We've got how many sessions left? 1, 2, 3. 3 sessions left. So we're going to start with some 7-mark questions. Start off with some nice easy organic chem and we'll go from there. I'll give you 2 or 3 minutes to think about each question, and then I'll give you my solution. So, start off with some nice, easy organic chemistry. So, 2 minutes, set my timer. If you want to start throwing some info into the chat, please do. So what you're doing here is you're basically just saying what you can see. This question does not require you to analyze the data. So what can you see? Right? Madison, no, what can you see just by looking at this? You don't even need to have chemistry knowledge. So to get 2 marks in this question, you would need to say the boiling point increases as the chain length increases. Ethane having the lowest boiling point. Alcohols having the middle highest. Carboxylic acids having the highest. So if you were sequencing this answer, you would write that. Then you would state also within the functional groups, as you increase the length of the carbon chain, you get an increase in boiling point as well. So that is how you would get 2 marks for that question. You don't need to go into the analysis. So when you're asked to explain, which is a cognitive verb, we like to use, but no one understands what it actually means. This is where you need to analyze. So what's happening to the boiling point as the chain length and by default, the molecular weight increases? What's happening to the boiling point in all 3 of those organic compounds? We have an increase in boiling point. So the trend that it's asking you to explain is that as you increase the number of carbon atoms in the chain and subsequently hydrogen, you're increasing the intermolecular forces. And what kind of intermolecular forces do we have between hydrogen and hydrogen? Bonus points for knowing that. Dispersion forces. So to explain the trend, you would say the chain length, as the chain length increases, so too does the boiling point. This occurs because of the increase in dispersion forces between the hydrocarbon backbones. That's how you would get 2 marks for that. So I'm going to let you, now we're looking at variations between the alcohols, carboxylic acids, and esters. Of the same molecular weight. So we would look at propan-1-ol, ethanoic acid, and methyl methanoate. So things to consider to get 3 marks in this. The type of bonding present in each molecule. That's probably half a mark. That's 1.5 marks there. If you can identify the intermolecular forces present between and link that to your explanation of this has higher boiling point. I'm going to give you guys 2 minutes to come up with an explanation for that one. Kai, what do we got? So Kai stated the number of hydrogen bonding sites. So I'm going to do a little bit of drawing on the whiteboard just to explain this. So esters, we've got a carbon to oxygen double bond. So it has dipole forces. If we look at an alcohol, we've got an oxygen to hydrogen single bond. So we have hydrogen bond. And as Kai has alluded to, there's a single site for hydrogen bond. On the end of this hydrogen is where you get bonding. A carboxylic acid has two hydrogen bonding as well. But instead of just having one site, you've got a site here and a site here. So you've got 2 sites for hydrogen bonding. And there's a technical name for this, Kai. What would it be? They form a specific type of molecule that you would need to state to get full marks for this question. A dimer. So explaining the variation, well, you can say esters have the lowest boiling point of the 3 because they only have dipole forces between the carbon and oxygen double bond. Alcohol is the second highest, or in the middle. It has hydrogen bonding, but only one site for hydrogen bonding. Carboxylic acids have 2 sites for hydrogen bonding on the end. So they can form what's called a dimer, and that's why if we compare propan-1-ol, we have 90 degrees Celsius. If we look at methyl methanoate, we've got 31.5 degrees. If we look at propanoic acid, we have 148 degrees. So you can see the difference there and the trend from low to high. Noah, yes, I would think to get, if knowing QCAA and how pedantic they can be, I would be putting the word diamond in there. All right, does that make sense? So stick to the trend of organic chem. I would say 3 out of your 7 or 8 complex unfamiliar or these kind of paper 1 questions are going to be organic chemistry. And they're often going to encompass multiple ideas. So we've got a synthetic pathway. So this is now our reaction pathways where we're oxidizing alcohols. Now, same thing. I'm going to give you guys a couple of minutes to have a think. Get your thoughts together on the process and we'll go through the answer. Hey, Madison, yeah, I will email the recording out after this. I'll upload it directly after the lesson. All right, Kai, kick us off. So we have a secondary alcohol that we're oxidizing. All right, Kai, what do we got? Well, it'd be butane 2O. So technically, correct enough. So when we have an alcohol, especially a secondary alcohol, let's draw butane 2O. Sorry, butane 2-ol. So we start with butane to ol. So carbon, carbon, carbon. So 4 carbons. We know the OH group is coming off the second carbon. And what the oxidizing agent, which in this case is potassium dichromate, that is what they will use. What it does is it gets rid of the hydrogen and creates a double bond. So it produces a ketone. So we would have butane to ol would be the name of the ketone. And the formula would be C4, how many H's have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the structural formula is kind of what we just did. So you guys are going to give 2 minutes to write the structural formula, draw the structural formula. So that's this. So I'm going to be nice and draw butane-2-ol for you. I want you guys to turn that into butane-2-O. So this involves knowing what so who remembers what potassium dichromate formula is? So it will be plus K2CrO7 minus plus H gives us plus H2O as a byproduct. So that's the structural formula for that reaction. All good? All right, let's look at some other, the final part of this question. So now this part involves some maths, which I'm going to hear lots of groans about later. So we're going to calculate the percentage yield of this reaction. You guys are going to have a think first, and we're just going to jump in and do it for you. So write down the information that we need. So you guys have got 2 minutes, and we're going to do the maths on the board to calculate the percentage yield. And this is what these big 7-mark questions are going to be like. It's not just going to be one concept. Some of these equilibrium and acid bases, like they're covered in the entirety of unit 3 and 4. Any ideas, Kai? So we need to calculate the number of moles of our alcohol first. So let's see if I can write with enough room. So we need to find the moles of butane 2O. So moles of C4H9OH. So to find the number of moles, to find the molar mass, we have 4 carbons, so 4 times 12.01. Then we've got 10 hydrogens. And 1 oxygen, which is 16. So the molar mass is 74.1. My calculations are correct. So molar mass, grams per mole. How many grams did we produce? In the question, 45, I think it was. Yeah, 45. So we take 74.1 divided by 45. What's that give us? Although I'm pretty sure I just put those around the wrong way. I'm smart. They're supposed to go around the other way. So we divide the mass by the molar mass. So 45 divided by 74, which gives us 0. We know from our reactions that we just made that we have a 1-to-1 ratio. So we've also got, 0.607 moles of butane 2O, which means if we've got a 1-to-1 ratio, we also have 0.607 moles of butane 2O. Because the reaction tells us we have a 1-to-1 ratio. What is the molar mass of our butane 2O? So we've got 4 hydrogens. So the M of butane 2O tells us we have 72.1. We can get that by doing the same as we did to calculate the molar mass. So I'm going to wipe this off the board. So we have things to remember. We've got 0.607 moles of butane 2O. How do we convert from moles to grams? So remember the molar mass of butane 2O is 0.607 is 72.1. We just times it together. So times by 0.607. So the theoretical yield, so remember when we're calculating percentage yield, we first calculate the theoretical yield based on the number of moles of the product that is present. We times that by the molar mass to cancel out the moles and leave us with the grams. So our theoretical yield is 43.7 grams. What was our actual yield that we got? So we got 30. So to calculate that, we do the actual yield of 43.7 over 30 times by 100. What does that give us as a percentage? Oh, it's the other way around. Sorry, it's my dyslexia. I blame it every time. So 30.0 divided by 43. That should give us roughly 68.6%. So if we were to write that out as a step by step, you would calculate the molar mass of both of butane 2-ol, butane 2-one. Figure out the number of moles of the reactant. Use the molar ratio from the balanced equation. Molar ratio from the balanced equation to figure out how many moles of product can be produced. In this case, it's 1-to-1, nice and easy. It's the same as the number of moles of reactants that we had. Just times that by the molar mass and divide the actual yield by the theoretical yield times by 100, and it gives you a percentage. Easy enough? Yeah, relatively. Right. Kai will be familiar with this question. So, who's familiar with the Haber process? Haber process, what do you want to call it? You should become very familiar with this if you're not familiar with it already. It will take it, I think it would be 8 marks out of your whole exam on this one process. So, Kai, or anyone, in these exams, if you are explaining something, use a chemical equation to explain it. What is the chemical equation for the Haber process? Any ideas? So, the balanced equation for, Kai's just put it in the chat. Very good. So, the Haber process takes nitrogen as a gas, hydrogen as a gas, in an equilibrium reaction, so the reaction is at equilibrium, and produces ammonia. We can balance it like this. It is exothermic. So the question asks, why do we need to carefully monitor the conditions that this reaction is happening in? Well, one, we are trying to produce as much ammonia as possible. That's the plan. That's the idea. That's what we want. It's exothermic. So we need to monitor three things. The pressure. Anyone tell me why we need to monitor the pressure? Temperature. Pressure, temperature, and the concentration of NH3. Why do we need to monitor these? What's going to happen if I drop the pressure? What's going to happen to the equilibrium if I drop the pressure? Which way is it going to go? So there are more gas molecules on the reactant side. If the pressure gets too high, the reaction will favor the reactants, and we do not want that. So we need to monitor the pressure so it stays high enough that the reaction is going forwards. What about temperature? Why would we need to monitor temperature? This is the important part. An exothermic reaction, when it's going forwards, is releasing heat. When the equilibrium is favoring the reactants, it's absorbing heat. So we want to keep the temperature low. I say low, it's still 450 degrees Celsius. That's pretty low for a chemical process like this. Let's go and do that. So if the temperature gets too high, the equilibrium reaction will favor the reactants, because when you jack up the temperature, the reaction will try to absorb the heat by going backwards. The concentration of NH3, which is our product, is really important. We can keep the equilibrium going this way by constantly removing the ammonia. There's also safety concerns when you're using high pressure. So you could effectively create a large bomb if the pressure got too high. If the temperature got too high, again, you're looking at a serious safety issue. So that's why we need to carefully monitor the conditions when we're producing ammonia. Okay. Let's find some more long answer questions, ones that have maths in them. I'm not confused. All right, let's do some galvanic cells. And hear the groans of misery. So where would we begin here? So what you should be doing is looking at the oxidation potentials and reactivity series of the metals. You'll find that zinc sits higher, and zinc will be oxidized. So I want you guys. So we've got a zinc electrode, and we've got a nickel electrode. So zinc has a higher reactivity than nickel. So zinc is going to start as a neutral compound. Because it's going to be what, Kai? It's going to be oxidized. Our nickel is going to start as a 2+ molecule because it is going to be reduced. So zinc becomes Zn2+, and nickel becomes just nickel when it's reduced. So I don't know if you can see on the board. So we start with zinc, it becomes zinc 2+, Ni2+ is reduced to Ni. So our two half reactions are zinc. So this is our oxidation. So we start with zinc with a neutral charge. We take 2 electrons away and it becomes zinc 2+. On the oxidation side, we have 2e minus plus gives us anion. So it's just the opposite of the oxidation reaction. If you go into your your formula book, what you'll see is that there'll be an electrical potential. Or the cell voltage under standard conditions, being 25 degrees Celsius. Anybody? You guys need to get to know your formula book very well. So chi, usually you'll make the biggest one positive. So you'll change the oxidation reaction to a positive number. Nickel. So we take 0.76, we add it to minus 0.24. So 0.52 volts. Now, to get the full 2 marks for this question, you would need to state oxidation, reduction, swap the largest one from negative to positive, and then take away the smaller number. So you'd end up with 0.52 volts. All right, here's a 4-mark question. So you are describing in this question and explaining the movement of particles from one side to the other, from the anode to the cathode. So where are the electrons flowing from? The electrons are flowing from zinc. So the electrons flow from the zinc electrode or the anode to the nickel electrode or the cathode. It always goes anode to cathode. And it's traveling through the wire connecting the two, through the voltmeter. So when the zinc atoms are oxidized, the Zn2+ ions will go into the solution. When this happens, the nickel 2+ or the Ni2+ will accept the electrons whilst in solution and then deposit themselves onto the nickel electrode. the reason we use a salt bridge, and this is really important, is because it maintains equilibrium. Or is it, in actual fact, I lie. It maintains just before equilibrium. We don't want the reaction here to hit equilibrium. Once it does, that means the battery is dead. So positive ions move towards the nickel half cell in the salt bridge. The negative ions move back to the zinc. So they're just balancing out the electronic charge. So there's 4. So you have to compare and contrast what happens at the anode and the cathode. That won't really change depending on the molecules. It doesn't matter what they are, it will still be the same. At the anode, you have electrons flowing from an oxidized metal to the reducing metal on the other side. In this case, it was nickel. Then you need to speak about the salt bridge and the movement of ions to balance the charge. Once the battery is dead and the charges on both sides are perfectly equal, the battery will not work. Okay. I will send you guys out these practice papers so you can go through them. They've got all of the responses. I'll also send my marked version of last year's exam as well. All right. How long is the time? Okay, let's maybe finish on this question. So, what's an amino acid? Anybody have any idea? What have we got on amino acid? No pressure. It's all in the name. So amino acids make up proteins. What makes up an amino acid? So, yep, so amino acids make up a protein. But here we're more looking at what makes up an amino acid. So an amino acid, you have, as Kai said, you've got an amino group on the left. And this is your N terminus. You then have an alpha carbon in the middle. We have a hydrogen. And we also have an R group. The R group tells us what amino acid it is, what properties it's going to have, what kind of protein it's going to have. On this side, we have our carboxylic acid. So if you're writing it, you're just writing H2N, CHR, COOH. Literally just write it out as that will be the general formula. So what kind of reaction do we get between two amino acids? So we get a condensation reaction. So we get a condensation reaction. condensation, production of water. So what happens is another amino acid comes along here. It's got its little NH group. What happens? Here we've got two H's and an O. So we get a condensation reaction which breaks all of these bonds, causes the release of H2O, and we get a bond between the neighboring, that's a terrible line, between C and N of the next amino acid. And this is called a peptide bond. So that's how you would draw the second answer there. So the type of enzymes that would break these bonds, because it's called a peptide bond, a peptidase is the enzyme that breaks down a peptide bond. Peptid, the peptide bond, ase meaning to break. So that's the enzyme responsible for breaking up the amino acids that we eat. And the last part of the question is what you guys are going to do, and then we will come back to it next week. So the question is, this is your homework question. Explain the differences between the primary, secondary, and tertiary structures of protein. So that's the question we will start with next week. Make sure I do it. And I will see you guys next week. So my question is compare and contrast primary, secondary, and tertiary. And I will see you guys on Tuesday.